Scanning and Tunneling Microscopy (STM). What is STM? It is an instrument which is able to take surface images at atomic level. The image shows a STM image of carbon atoms taken by Dr. Shamika. So you may wonder, what is tunneling? Classically, if one wants to move a boulder over a mountain, he would need to climb up the mountain to reach the other side. And tunneling would refer to the stone simply tunnel through the mountain to the other side. This is only possible if the width of the mountain is narrow enough. Using the boulder as an analogy, we now look at the case of an electron which is traveling in a wave-like form. The width of the wall is the energy barrier, and if it is large, no electron is able to pass through it. However, if the energy barrier is reduced significantly, some electrons may have sufficient energy to tunnel through the energy barrier. This is the main working principle in STM. Now, I will show you the main components in the STM equipment. First, we need a probe made of conducting material and a sample for analysis. The conducting probe is important to allow current to pass through, and the tip has to have only one atom to give good image resolution. STM has to be sensitive to small change in detection signal, hence an amplifier is required. The last main component would be the computer, which shows the data in the form of an image. After introducing the main components, we need to set up the equipment for analysis. In some STM equipment, the probe is synthesized to one atom tip by chemical reaction, but in this case, we prepare the tip manually using platinum iridium wire. We will be analyzing HOPG sample. We also need a magnetic sample holder. A wire cutter to cut the probe and the storage tip to cleave the HOPG sample. So, you may wonder, what is HOPG? It is known as the highly ordered pyrolytic graphite. This material is similar to graphite, which made up of carbon atoms, but their atomic arrangement is different. Graphite is made up of carbon atoms arranged in a layered structure. The interlayer attraction is weaker as compared to the bond between the carbons lying on the same layer. Similar to graphite, HOPG also has a layered structure. However, HOPG is preferred over graphite for analyses because of its highly ordered arrangement between layers and high purity, as compared to graphite's random arrangement and defects in the structure. So, how should we prepare the HOPG sample? Because of its layered structure, we can clean the surface of HOPG using storage tip to cleave the top few layers. The sample is ready for analysis when the surface is clean and smooth. Next, we prepare the STM probe by tearing the platinum iridium wire in the direction parallel to the wire to ensure the tip will be sharp with one atom. In this experiment, we will be using the NanoSurf Scan 2 controller. And this is how it looks like. The controller is also equipped with a scan head to put sample and wire. There are many other types of STM equipment. Why do we choose NanoSurf Scan 2 controller? Firstly, it is because this is portable. And in terms of cost, this is considered one of the cheaper ones out in the market. Lastly, this equipment is good enough for teaching purposes. However, because of its small size, it is prone to vibration interference during analysis. Also, because the tip has to be manually prepared, the resolution of the image may be affected adversely. Hence, although NanoSurf Scan 2 controller may not be the best, it is able to fulfill the learning objectives of this experiment. So after we have prepared the tip and the sample, we are ready to place them in the scanning head. This is the scanning head which we will be placing the tip and the sample in. The arrow indicates the position of the scanning tip is being placed. The HOPG sample will be placed on the magnetic sample holder and placed in the area shown. This is the final setup at the scanning head. Looking through the magnifying glass, we can see the tip and the HOPG sample. They have to be very close to each other, but yet not in contact. With that, we need to use the software to bring the tip and sample closer to each other. By visual, the sample and the tip seems to be in contact. However, it is not if we zoom into the portion. From the diagram, the space between the sample and the tip is very small. Only then, tunneling can work. Previously we mentioned that if there is a barrier in front of the electron, and if the barrier is thick, no electrons can pass through. Now, taking the space between the tip and the sample, indicated by the red area, this is like the barrier which the current have to overcome in order to tunnel between the two. Hence, by moving the sample towards the tip, we reduce the spacing, and so tunneling of the current is possible when a voltage is applied. With that, tunneling will not occur if the spacing is large. So it is important to bring the sample closer but yet not crashing into the tip. So now, we're ready to scan our sample. A voltage will be applied, and current will flow from the tip to the sample surface and the parameters are being measured. There are two types of scanning modes. The first one is the constant current mode, which measures the high displacement of the tip at constant current. As such, the tip moves up and down to maintain the constant current flow in the system. And the second mode would be measuring a constant height with varying current. The height of the tip will be the same throughout the scanning, and the current will vary according to the spacing between the surface and the tip. Between the two modes, if the sample is not flat, it is advisable to choose the constant current mode to prevent crashing of the tip. Once everything is set, we can now scan the sample. This is how the sample is being scanned. The blue lines represent the movement of the tip across the sample. So this is the first zoom-out image we need to find. This shows a terrace indicated by the arrow, then we zoom into the terrace and get a 3x3 image of carbon atoms. This is what we expected, but we got something like that instead. Although the resolution is bad, we still can see the arrangement of these 7 atoms being circled. These 7 atoms are actually carbon atoms. Looking at the center atom, we can see that it has 6 neighboring atoms around it. So why do we observe such arrangement in the image? This is how the carbon atoms are being arranged in one layer of HOPG sample. They are arranged in hexagonal, but one atom only has 3 neighboring atoms instead of 6. So now let us stack the second layer directly on top of the first layer. We would actually observe the same thing. But if we were to stack the second layer by the AB arrangement, it would appear to be staggered. And now we observe something different. In STM, image is churned out by measuring the amount of current, which is also dependent on the electron density of the atoms. With that, in this staggered arrangement, some atoms in the second layer are overlapping the atoms in the first layer. This is indicated by the red circle. Therefore, the 7 atoms we observed in the STM image are not exactly adjacent atoms. With that, how can we improve our resolution of the STM image we obtained in this experiment? Firstly, we can make the scanning tip sharper. A blunt tip will cause interference in the current received, as now tunneling can occur at many atoms instead of 1. Hence a sharper tip would ideally mean to have only 1 atom of the tip, which would improve the resolution. Next, we can try to have a cleaner and flatter sample surface. Any contaminants can affect the scanning process, hence it is advisable to clean all tools using ethanol. A flatter surface would also ensure that all atoms are planar and have the same distance from the tip to allow a more accurate scanning. Therefore, we should clean the HOPG sample several more times. The last suggestion would be using another imaging method known as atomic force microscopy. AFM is also an imaging method widely used in nanotechnology because it has a tip which touches the surface atoms, resulting in an image of higher resolution compared to STM. So for this experiment as a whole, we can conclude that STM indeed able to provide atomic level imaging. And the working principle is to measure the current tunneled from the tip to the sample when a bias is applied. It is good to prepare a clean and flat sample for analyses, and that a sharp tip is prepared for platinum iridium wire. HOPG is usually preferred over graphite because of its automatic arrangement. The nanosuperficie scan used here is portable and easy, but prone to interferences. However, it is good for teaching purposes. The image taken by us proved that the tip has to be very sharp in order to produce image with good resolution. And lastly, other than STM, another imaging method could be AFM, which should be able to give better image. Now, we've come to the end of this report. We hope you enjoyed it as much we had when we were doing this experiment with Dr. Shamika. We would like to thank the following website and references which helped us to complete this multimedia report. Thank you for your time.